Today we're going to simulate a Falcon 9 satellite deployment mission. As you can see, we have our vehicle on the pad here, as well as our launch tower and our launch control legs. Looking at our launch for today, we're going to start with our liftoff process at T-0. And during this initial burn on our first stage booster, we're going to go through the process of max Q. Max Q is the maximum dynamic pressure that our vehicle is going to experience during liftoff and ascent. As you can see here, we have dynamic pressure on the vehicle, air density, and velocity. And at the beginning of our flight, before we get higher into the atmosphere and at a higher altitude where air density is lower, we're going to experience a high amount of air density and a lot of pressure while we are accelerating. And this is going to put the maximum amount of strain on our vehicle as we ascend through the atmosphere. So the point where we have max Q is where these three values are all kind of overlapping. And we can see our maximum threshold for dynamic pressure is here. And that's before these two values overlap, but the maximum pressure is right at about 12 kilometers here. So once we get through max Q, we're going to have our main engine cut off, and the stages are going to separate, and our second stage is going to continue on its way until payload separation and deployment. But our first stage booster is going to begin its reorientation back towards the launch site and begin a boost back burn to deaccelerate and begin its retrograde trajectory. As the booster descends through the atmosphere, we're going to have a re-entry burn, which is going to help us burn off some of that extra velocity and speed, and also to protect the booster from the heat of re-entry. Once we get through the thickest part of the atmosphere and we start to really deaccelerate as the atmosphere continues to get more dense, our grid fins will deploy, and when we get about 3.5 kilometers above the launch site, we're going to begin our landing burn. We'll have our grid fins and our landing legs deploy, and we'll have a soft touchdown. Note that on this graph, on this image, we are landing on a drone ship, but for today's launch, we'll be landing back at the launch site. So looking at our staging here on the left, we're going to have our first stage with our Merlin engines and our control legs. The reason we have it set up this way is to allow us to begin throttling some of the engines before we release the vehicle and allow it to start accelerating and ascending. And we do this so that the vehicle doesn't fall to the launch pad because there's not enough thrust. And then there's also some of the staging icons here that need to be rearranged. So on our second stage, our payload icon was there, and that's our payload fairing. It allows us to separate the fairing and release the satellite. And that fairing protects the satellite while we're accelerating out of the atmosphere. So we're moving that to the payload stage and moving some of these other icons like our separation systems to the second stage, which is going to help us separate our second stage from the first stage when we have stage separation in flight. So going through here, we're just making sure that our decouplers are staged before our second stage engine ignites. If we didn't do this, the second stage engine would ignite before we released the second stage from the first stage, and that would result in a rapid explosion and loss of the vehicle. We're also going to look at our atmosphere bar and sensors up here. So this is what allows us to see the density of the air while we're increasing in altitude. This is going to go down. We also have our altitude meter right above it, which is what's going to allow us to see our altitude. This is the setting that allows us to change control back to the first stage booster after stage separation. And on the left here, we have our time warp bar, which we'll use at some point as well. And down here, we have our gyroscope. This is what allows us to see our orientation and trajectory during flight. We have our stability augmentation system, which allows us to change different trajectories. Right now, we're just in stability assist, but there's also prograde and retrograde. For most of flight, we'll be using prograde, but when we return the booster later on in flight, we will be using retrograde, and I'll explain these concepts later. We also have our reaction control thrusters, which use monopropellant to activate small thrusters that we can use to change our orientation. All right, and with that, we're ready for launch. So we're going to throttle up here and ignite. So we're going to start accelerating and picking up speed and altitude. We want to make sure that we get away from the launch pad before we start doing any of our maneuvers. So we want to try and get to like 1,000 meters and 100 meters per second in velocity before we start pitching downrange. And downrange is just going to be prograde, which is going to be in the direction of orbit. And as we can see on the nav ball, that little yellow circle that we're navigating around with our orientation is prograde. and that's sort of the orientation that we're sort of aiming for here off launch. So as we're gaining altitude, we can also see that our air density is going down. And as we pick up speed, this is going to progressively allow us to accelerate further and more efficiently as there's less drag on the vehicle. You can see the moon there as well. So we're getting pretty close to max Q here. This is again the highest point of pressure on the vehicle as our velocity is increasing while air density is still relatively high. And we're still pitching down range here, and we're getting pretty close to the point where we can talk about our gravity turn. After liftoff, the rocket begins a maneuver known as the gravity turn. Rather than continuing straight upward, the vehicle starts to shift some of that velocity horizontally. This is important because reaching orbit isn't just about gaining altitude, but building enough sideways velocity to continually fall around the Earth. Here we have prograde and retrograde orbit. So with prograde orbit, the vehicle in this instance is accelerating in the direction of the planetary rotation, versus with retrograde orbit, we are accelerating opposite the direction of planetary rotation. So what this actually looks like with our vehicle is that when we're accelerating in a prograde orientation, a prograde trajectory, our orbital altitude is increasing. So we are going to have a higher orbit farther away from the surface of the planet, versus with a retrograde orbit, our vehicle acceleration is going to cause us to have a smaller orbital altitude and actually orbit closer to the planet. And this is important because it allows us to burn fuel more efficiently and use more of our delta V without wasting any of our efficiency or fuel. So jumping back into our flight here, we're going to continue with our first stage burn. We're going to continue that gravity turn and just gradually pitching the booster downrange. And we're also getting pretty close to stage separation here. As you can see, our fuel's low, so we're going to throttle down our engines. This is main engine cutoff on the first stage. We're going to separate and start ignition on our second stage. So we're going to continue our trajectory on the second stage as our altitude continues to increase, and we're going to keep doing that gravity turn as well. The second stage engine uses a vacuum optimized engine with a much larger nozzle or engine bell than the engines on the first stage. In space and high altitude, there is little to no atmospheric pressure pushing down on the exhaust plume, and so it expands a lot more. So we can have a more efficient optimized engine bell that is wider in space and gives us more efficiency when we're burning fuel, and gives us a higher energy efficiency on our stage. And this is really important for the long duration burn of the second stage. At this point, our stage trajectory is almost entirely horizontal. And again, as we were saying earlier, this is just to increase our velocity horizontally as we continue to accelerate around the planet. Not really trying to increase our altitude as much anymore, as we are just trying to increase our speed so that we don't re-enter the atmosphere and burn up. So as we continue to accelerate, we're getting pretty close to orbital velocity now, as we can see on the map. And we'll reach this blue stable orbit, and we can throttle down and begin our payload fairing separation. So as we deploy our payload and accelerate it away from our second stage, we can begin to deploy our solar panels and some of our equipment on our satellite. Our second stage and fairings are going to fall back into the atmosphere and burn up on re-entry. So we can deploy some of these systems. We have our solar panels as well as a couple scientific experiments. These are just for demonstration today, just to give an idea of some of the things that we can do in Kerbal, and just to demonstrate some of these concepts. To celebrate our satellite deployment success, we're going to launch off a quick little JMU themed firework in space. This isn't super realistic, but just for fun, and to celebrate that we've achieved our payload So we're going to go back and demonstrate the first stage now. So as you can see, our second stage is going to accelerate on its way, and we basically just went back in time a few minutes to simulate the first stage booster. So using our reaction control thrusters here, we're going to reorient the booster back towards the launch site before we ignite our engines for the boost back burn. Our reaction control systems use monopropellant as the fuel source, and they ignite this and combust it and use the pressure to change the orientation of the vehicle. So we're almost back to trajectory now, and we're going to switch to map view. And when we use this, we can see this big red X, and that's what we're going to use when we ignite our engines here. So you can also notice that we're using 3 engines now. We've deactivated some of our other engines to conserve fuel. And we're just going to use this trajectory bar to orient and make sure that we're landing above the launch site. So we will shut down our engines when we reach this point. On real Falcon 9 missions, this entire process is automated with a computer system, but we don't have access to that in Kerbal, so I'm demonstrating this for you manually and doing these trajectory calculations and changes. Here we're changing our orientation to get our booster engines back towards the ground for when we do our landing burn. And we're going to use our retrograde orientation as we fall through the atmosphere. So now that we're in retrograde orientation, we're just going to descend through the atmosphere, and we're going to start accelerating while we're still at a very low air density. And this is going to continue to increase until we reach a thicker part of the atmosphere, and that's where our air braking is really going to kick in and help us deaccelerate. So now we're beginning to enter the thicker parts of the atmosphere, and as you can see, we're starting to deaccelerate, and that air braking is kicking in. So we're going to wait until we're at about 4,000 to 3,500 meters before we start our landing burn. So we're getting pretty close to 3,500. So we'll start igniting for our landing burn and rapidly deaccelerate. And our thrust is going to fluctuate a little bit as we throttle up and down. We're trying to make sure that our meters per second gets to about 40 to 30 meters a second before we switch to one engine for final touchdown. So again, we get down to 32, 33 meters per second, switch to one engine, activate our landing legs, and slightly throttle down for landing. And there we go. So today's mission was a success. We made it through stage separation and payload deployment and recovered our first stage booster as well. I hope you guys learned something today, and I appreciate you watching. Thanks. Go Dukes!